Parallel forces. There are some forces which are in such a way that their lines of action are not parallel to one another, that their lines of action do not meet. Such forces are said to be parallel forces. And when you have parallel forces and you want to get their resultant, what you do, you take one direction to be positive and then the other one as negative, and you get the algebraic summation. And the algebraic summation thing, I have already talked about it, where one direction must be positive and the other one to be negative. We have this particular example here. If we want to get the resultant of these forces, we can take the upward forces to be positive and the downward forces to be negative. So we get the sum of those forces, and particularly not just the sum, but the algebraic sum. So we have 8 plus 6, that is for the upwards, plus negative 6 plus negative 5. So we have this one as 14 plus negative, this one is negative 11, and we have this is F. We finally have that F is equal to 3 newtons. That means that the resultant force is acting upwards because it is positive, and our assumption was that the upward forces are positive, downward forces are negative. So by getting a positive force, it means that the resultant force is acting upwards. We have under parallel forces, there is what we call a couple. Understand that a couple refers to two equal but opposite forces not acting along the same line. Equal and opposite. If we just say equal and opposite, I can have this force acting on this particle, and then I have this. Then I have that one F and that one F. These forces acting like that are not constituting a couple because they are acting along the same line. But forces which are not acting along the same line and they are parallel and they are not equal and they are equal, I say it constitute what we call a couple. So the line of action of this force is along with that, and it is parallel to this one here, and the forces are equal. What is special about a couple is that they create a rotation effect. An example of a couple can be exhibited in when you are on the steering wheel. The forces your hands apply on those wheels is constitute a couple. So they create a rotating effect. And as now I said that if the resultant of a system of forces is 0, either there is no force or it is a couple. That is what we need to know. That if you have that the resultant of a number of forces gets such a 0, then it is most likely that those forces constitute a couple. That the forces are equal in opposite directions. Then we have this term, moment of a couple. Oh no, moment of a force. This one is moment of a force. It is some concept we talk about when we are dealing with the statics of a body. So what does the term moment of a force mean? Does it have anything to do with the time? The answer is no. It doesn't have anything to do with the time here. But we are saying that the moment of a force about a point is found by multiplying the magnitude of the force and the perpendicular distance from the point to the line of action of the force. So this one is the force here. You have the force F, and if you want to get the moment of that force about the point O, you get the magnitude of the force, which is F, multiplied by the distance between perpendicular distance of the line of action of the force from the point. So basically here we can say that moment of the force is F times F times D. That is moment of force about O. We can write and say that moment of the force about O, something like that, is equal to, then we have this one here. So that is moment of a force. Just a matter of, it is the product of the force and the perpendicular distance of the line of action of the force from the point. That is what we call moment of a force. Let's have a look at this example. Consider road AB shown below. Now this road is from A to B. It is a road of 3 meters because we have these two and this one. And if you apply a force at B, find a moment of 5 Newton, this force here, about A, about this point, when it is applied at each of the points B, C, and A. So if you apply this force of 5 Newton is at a point where it is right now, at point B, the line of action is already perpendicular to the road in question. So with this one is force at, we first of all have force at B. Moment about A is equal to product of force and the perpendicular distance of the line of action from the point. So this one is 15 Newton meters. This type of motion is anti-clockwise, and with the force at C, we have that moment about A is equal to force times when the force is at C, the same force acting at C, 5 Newton force acting at C, it shall have a turning effect about A, which is equivalent to 5 times 2, and this one is 10 Newton meters, still anti-clockwise. Then when you have the force, when the force is at A, moment of force about A is equal to force times, you realize that the perpendicular distance of the 5 Newton force about A is this time equal to 0. So we simply have 5 times 0, which is equal to 5. And there we are. This one is an indication that a force cannot bears no moment about a point where it is passing. So if the force passes through the point A, then it doesn't bear a moment about that point A. That's what we need to know about moments. Algebraic sum of moments. If a number of coplanar forces act on a body, their moment about any point may be added, provided due regard is given to the sense of each moment. Still, we are having coplanar forces. What someone may be interested in know what are coplanar forces? These are forces that act in the same plane. Coplanar, they act in the same, they lie in the same plane, and we can add them. If we talk about moment of such forces, we can add them, and we are saying that regard must be given to the sense, and that means that we still have algebraic sum, that whenever you have positive, like you can have clockwise moments to be positive and then anti-clockwise moments to be negative. We have an example. They are saying that forces of 2 Newtons, 3 Newtons, 5 Newtons, and 7 Newtons act along the sides A, B, B, C, C, and D, A of a square A, B, C, D of side 2 meters. Find the moment of each force about A. Find the algebraic sum of moments of the forces about A. Then comment on your on your result. This one is an outline of it is a sketch of of the way the forces are acting. Now we have the force and then the moment about A. I shall start with the force 2 newtons. That force passes through point A because this is the point A, and the 2 Newton force passes through that point, so it has no moment there. 2 times 0, which is equal to 0. And then the other force is, I can look at the 3 Newton force. Now the 3 Newton force has this one as its line of action, and the perpendicular distance of that line from the point A is the distance AB, or actually it is AB, which is supposed to be 2. They said 2 meters for every side. Every point is 2 meters. So it is the force, which is 3 newtons, force 3 times perpendicular distance of the line of action of the 3 Newton force from A, which is equal to 2, getting us 6 Newton meters. The other one is a 5 Newton force. This force has this one as its line of action. It is acting along with that line, and perpendicularly that line is at a distance of 2 meters from the point A. So force times perpendicular distance from the point A to the line of action of the 5 Newton force. So we have 5, which is the force, times the distance, which is equal to 2, getting us 10 Newton meters. The other force is the 7 Newton force. 7 Newton force. It is passing through A. So if you try to get the perpendicular distance of the line of action of the force from point A, you cannot get it, because this is the line of action of the force and it is passing through A. So the perpendicular distance of the line of action of the force from A is 0. So that is 7 times 0, which is equal to 0. And now sum of moments, if we are to get the sum of moments, is this is sum of moments. You can write this, sum of moments is equal to, we have 6 plus 10 plus the other zeros. It is equal to 16 Newton meters. What I can say about these moments is that they are clockwise. They are clockwise moment. The resultant moment is anti-clockwise. That's what you can say. Resultant moment is clockwise, because as you can see, the 6 Newton meter, the 2 Newton meter force is having 0 moment. But this type of moment here, we are talking about the turning effect of this force about this point. It is clockwise. And the turning effect of this force about the point A, this force like this, turning point here, the turning moment is turning effect is still clockwise, because this force will tend to turn this length here and the clockwise direction. So the resultant moment is clockwise. Moment of a couple. And now if the magnitude of each force forming a couple is P newtons, and the perpendicular distance between their lines of action is A meters, the magnitude of the moment of the couple is PA. So like here you have the forces, this one, that one, they are parallel forces and they are acting in opposite directions. So basically they constitute a couple. Now the distance between the two forces is A. Now to get the moment of a couple, you get the moment of a couple is the product of one of the forces and the perpendicular distance between the two forces. So just get one of the forces and you multiply with the perpendicular distance between them. They have written there is this statement here: the turning effect of a couple is independent of the point about which the turning is taking place. Let us try to do this. Let us extrapolate this one to a certain point O, where this point is this one is D. The distance from here to there is D. Now if I take moments about O, for this force here, it is PD, and this one is anti-clockwise. Then the moment of this force P about O is P into A plus D, and this force is clockwise. If I want to get the moment of I should take the sum of the moments about O. So the sum of the moment of this couple, which is this one and that one, the sum of the moments about O for this couple is given by P into A plus D minus PD, which is equal to PA. So we are saying that whether you take a moment about whatever the point, you shall have that the moment is equal to P times A. It doesn't matter which point you have taken the moment about. There is this example where they are saying that show that the system of forces given in the diagram forms a couple, and find the moment of this couple. Let us try to resolve the forces parallel to the 7 Newton force. I look at upward forces equal to 7, downward forces are also equal to 7. So basically, we saw that what does it mean to have a couple is when the resultant of the forces is 0, then you can have that the force, if the forces exist and you have that the resultant is 0, then that force is that one is a couple. So 7 upwards plus -2 plus -5, you are getting 0. So that for that the system of forces here constitute a couple. And they said find the moment of this couple. We saw that moment of a couple doesn't mind whether you take it for about whatever point, you get the same thing. So we are going to take the moment about the point A. Take moments about A. The 7 Newton force has no moment about A. This one has a moment clockwise, and this one also has a moment clockwise. So we have that moment of couple is equal to 2 times 1 plus 3 times 5. Not 3 times 5. It is 2 times 1 plus, because this force is at a distance of 1 meter from A. While for this 5 Newton force, the distance from A is this 3 plus this 1. So this one is 5 times 4. We are going to get 22 Newton meters. That is the moment of that couple. So the forces form a couple with a moment 22 Newton is in a clockwise sense. That is what we can say about that. Here we have a case of parallel forces in equilibrium. What happens is when the forces are parallel and are in a state of equilibrium, that one shall mean that maybe if you have forces in the vertical sense, shall have that upward forces are equal to downward forces. That is one thing. Forces to the left should be equal to the sum of forces to the right. And then the other thing which applies that the sum of moments in the clockwise sense should be equal to the sum of moments in the anti-clockwise sense, provided you are taking the moments about the same point. Those are the conditions we are going to be using for bodies in equilibrium, for parallel forces in equilibrium. We take a moment, and after some of those conditions are also correct for even other forms of coplanar forces. So around here we have a uniform beam of length 2 meters and mass 4 kg, has a mass of 3 kg attached at one end and a mass of 1 kg attached at the other end. Find the position of the support if the beam rests in equilibrium. We need to make some diagram here that can enable us solve this problem. A uniform beam of length 2 meters. That one is from this point. That's the beam. They say the beam has a mass of 4 kg. So because it has a mass and it is a uniform beam, this word is important. It's not being put here for granted. A uniform beam shall always have its center of mass in the middle of that beam. So if it has the length of 2 meters, at exactly 1 meter from either sides, we shall have the weight acting there. Because of this 4 kg, we have a weight 4g acting in the middle. And if the weight is there, and on one side you have 3 kg giving rise to 3g newtons, and one side you have 1 kg giving rise to 1g newtons, the support is supposed to be somewhere close, nearer to the heavy weight, so that for this other side, since it is since this side is small, shall have that the weight will be compensated by the longer distance, so that you can have a bigger moment because it is a smaller force. So this is precisely what we have. And now what we are going to do, first of all, they want us to get they said find the position of the support position. That is the point, that is the x which we have there. What we are going to do, we can just take a moment about the point, about the support, taking moments about if this point is C, can call it C. So taking moments about C, we shall be eliminating P from the moments, because P is passing at that point. It has no moment about that same point. So this moment is anti-clockwise, this one is clockwise, and this one is also clockwise. So we have that the sum of clockwise moments about the point C is equal to the sum of the anti-clockwise moments. So we have that 3g x is equal to 4g. Now if this distance, remember this whole thing has 2 meters, so from here to the end it is 1 meter, and from still the middle to the end it is 1 meter still. So this C, from C to the middle, it is now 1 minus x. It should be 1 minus x, such that when I add this one plus the x, I get the 1 meter. And so this is 1 minus x plus 1g into, now from this point to the point C. Remember the whole thing is 2 meters and I've just removed this x. So from C to this point here, it is 2 minus x. I have the whole 2 and I'm just subtracting the x. I work out this one, g will cancel everywhere, and I have 3x equal to 4 minus 4x plus 2 minus x. When I try to add up all the x's, I'm going to get this side 5x, the other side 8. So I have that 8x is equal to 6, giving us an x which is 3 over 4. So the position of that portion is 3/4 meters. This one is in meters. It is 3/4 meters, 0.75 meters from the end where you have put the bigger force. Another person can use the fact that the sum upward forces equal downward forces, and after getting the value of P, you go ahead to get the moment about any point. Somebody can get a moment about this side, this point here. I can call it, let me label this one A, label this one B. You can take moments about A, you can take moments about B. But now if you take moments about A, you are going to need to find the P and X. So you can find the P by summing up upward forces and equating them to downward forces. The example 2 is saying that a light horizontal beam of length 2 meters rests with its ends A and B on smooth supports. The beam carries masses of 5 kg and 2 kg at distances 60 centimeters and 150 centimeters respectively from A. Find the reaction at each support. I'm going to make, actually I didn't leave space here. You are going to excuse me, I'm going to use the space down here. I'll be using this before you can look at the non-parallel forces in equilibrium. Shall use this space to work out that. This one is the analysis of, that is the diagrammatic version of this thing. A light, this word is not for fun. Whenever they tell that a beam is light, it means that its weight can be neglected. We are not going to consider its weight because it's a light beam. So in mechanics, particularly if they talk about something being light, it means that it bears a negligible weight. If something is inextensible, then it cannot be, it is inelastic. If something is uniform, then it is something whose center of gravity lies in its center, at its center. So this beam is having length 2 meters. So from A, 5 kg is put at the point where we have 60 centimeters from A. Then 2 kg, this one is 2 times G. This is 2 kg. The weight is 2 times gravitational acceleration. So it is at a point where we have 150. It is being got from 0.9 and 0.6. The first 0.6, you add on 0.9 to get the 1.5 meters, which is this one. Then the remainder, since there are 2, and this is 150 from A, the remainder should be 50 centimeters towards B. And the 50 centimeters is the one we are having here as 0.5 meters. Now at the pegs, at the supports, we shall have reactions, because this peg, this beam is exerting a certain force on the supports. The supports are going to exert the reaction is R1 and R2, and particularly upward forces equal to downward forces. So you sum up the upward force and they should give us the sum of the downward forces. So we have that R1 plus R2 is equal to 5G plus 2G, implying that R1 plus R2 is equal to 7G. You can call that equation number 1. And then after that, we can take a moment. We shall take a moment about the point A. Now, if we take a moment about A, we shall be doing away with the R1, because for it is actually for it that R1 is passing through the point A, so it has no moment about A. So we shall have 5G, the force, the distance of 5G from A is 0.6, plus the 2g times the distance from A to point 2g, the distance from this force to the point A, it is 0.6 plus 0.9, which is 1.5 meters. Those are clockwise moments about A. They should be equivalent to this one, which is providing an anti-clockwise moment. So this is R2 times, that one is actually 2 meters. So we have this one as the G. Oh, there is G everywhere, not everywhere. There is no G there. So we have this one as shall have 3G plus this one is another 3G equal to 2R2. 6G equal to 2R2, and this one is implying that R2 is equal to 3G Newtons. And now from equation 1, we have that from 1 we now have that R2, which is 3, R1 plus R2, which is 3G, shall get 7G. And this implies that R1 is equal to 7G minus 3G, which is 4G Newtons. You need to substitute back the values of G and write them as write the final answer as a decimal number. That is what we have there. Check it out. There is a statement here about non-parallel forces in equilibrium. When you have non-parallel forces and they are in a state of equilibrium, then we are saying that still we use the fact that algebraic sum of moments of the forces about any point is 0. That is what we use. And we have this example here. A pendulum of mass. A pendulum AM consists of a string of length 2 meters and a bob of mass 5 kilograms. The pendulum is suspended from A and held in equilibrium by a horizontal force F applied at M, so that the string makes an angle 30 degrees with the vertical. Find the force F. I need to get you a diagram which you can relate, which you can use to solve the problem. There we are. That is the diagram. The bob is here and the string is there. They said the string is making an angle of 30 degrees. Held in equilibrium by a horizontal force, which we are calling F, applied at what? At M. We have that horizontal force acting there. That one cannot stop the weight of the bob from acting vertically downwards. So basically those are the forces. Because of this force and then this weight of the bob, there will be a tension which will be put up within the string. And what we are going to do, if I will assume that point M, the pendulum, the bob is at a distance x from the point of suspension, and at a vertical distance y, then we have we can get the values of x and y, and we can think of taking moments. Take moments about the point. Let's take moments about A, because what they want us to get is the force F, just the force F. So that is not necessary. They don't want us to get T. So Y, they say the pendulum is of length 2 meters. So I have 2 meters. And Y is adjacent to this, and this is hypotenuse. So Y is equal to 2 times the cosine of 30 degrees, while x is equal to 2 sine of 30 degrees. So we have that taking moments about A, we shall take moments about the point A. If we do that, we have that clockwise moment equal to anti-clockwise moment. The clockwise moment is the moment due to this force here. So we have 5g times x, the distance, the vertical distance, the perpendicular distance of the line of action of that force. That is the line of action of the force. It is acting along with that line, and the distance from A to that line is the same as this distance x. So it is x. Then F is acting along with this, and the perpendicular distance of the line of action of F from the point A is y. So we have F times y, and so we have 5g into this one is 2 sine of 30 degrees is equal to F, the one I'm looking for, times y, which is equal to 2 cosine of 30 degrees. You can see that here you're going to get that F is equal to 5 times g times 2 sine 30 degrees divided by 2 cosine of 30 degrees, which is equal to 5g times tan of 30 degrees. And if you work out that, you're going to get 5g and the square, and the tangent of 30 is 1 over root 3. And when you work out everything at the end of it, substitute for g. This is 5 times 9.8 over root 3. The calculator is going to get us something like 28.3 Newton. Is that happens to be the value of F. We have this example. A uniform beam AB of mass 100 kilograms and length 2L has its lower end A resting on rough horizontal ground. It is held in equilibrium at an angle of 20 degrees with the horizontal by a rope attached to the end B, which makes an angle of 40 degrees with BA. This is the situation we have. This angle here is 20 degrees. I'm indicating some bit of a frictional force here because the road ground is rough. There will be some friction in that direction, and there is tension. There is a tension in the rope, and then because the beam is it a beam? Yeah, the beam is uniform. We have its center of gravity acting in the middle. So since it is 2L, this is L, and even this is L. So you have L, a half of the 2L. So it is in the actual middle, L and L. So what we are going to do is to take a moment about the point about A. We take moments about A, and we have, if I call this side A, then I can call this side B. This side here, I'm calling it B. The length is the one I'm calling B. From point A to where the weight is crossing there, to the line of action of the weight. So we shall take a moment about A. Take moments about A. That's how we can write that thing. That one means taking moments about A. That's what it means. So we shall have that clockwise moment. The sum of clockwise moments is equal to the sum of anti-clockwise moments. So the clockwise moments we have the 100 G Newton force multiplied by this distance here. It is this side is the hypotenuse and it is L. Then this one is adjacent, so we have L times cosine of 20 degrees. It should be counterbalancing the T times this side is opposite to this 40, with this one as the hypotenuse, 2L as the hypotenuse. So we have this one as 2L times sine of 40 degrees. And from there, we are going to get the value of T. T is equal to 100 times G times L times cosine of 20 degrees divided by 2 times L times sine of 40 degrees. When you work out this, you're going to get 100 times 9.8 cosine of 20 degrees divided by 2 sine of 40 degrees. There are those which cancels, but at the end of it, you are going to get 716 newtons. That's what we have there. This number is similar to the one we have just done. It is similar to example 2. So I want you to try to show that the tension is equal to mg divided by root 6. You try to work it out. Submit your answers. You just get a photo of your working and you send it to me from the Telegram channel there. I try to look at it and see whether you are progressing. Peace.